So the reaction I'm working with is reaction 3B. So the first thing to do when tackling this problem is to look at what we have here. And we've got this C double bond to O carbonyl group, so that carbon's very electrophilic. Furthermore, there's a nitrogen there, so this is an amide functional group, and we're forming a carboxylic acid. And then there's acid and water, so that will determine our steps. So now that we've identified what we're working with here, the first step is for that carbonyl oxygen to attack the hydrogen off of hydronium. This makes that carbon super electrophilic, and which will lower the LUMO and make it easier for our preceding steps to happen. And that's really what happens right there. That attacks that, forms these. So the next step is to break that pi bond, which means adding into that pi star. Basically, what I mean by adding it to the pi star means we're adding it to an antibonding orbital. Just as we can see here, electrons get kicked down to an sp3 orbital, which forms our bond angles of 109.5 degrees and our carbon tetrahedral. And that's what happens right here. Water comes in, and it adds into that. As you saw in the previous step, now that water has added, we have a positive charge here. So we're going to have a water molecule come in here and take off one of these hydrogens and form H3O+, which then forms this OH here, which has a neutral formal charge. So now the next step is to make nitrogen a better leaving group, and we're going to do that by having nitrogen, that lone pair, attack this H on this hydronium, and it forms this new compound with nitrogen with a positive formal charge. It's a better leaving group now. So now that nitrogen has been made a better leaving group, we can go ahead and proceed with the eliminating / ring breaking process here, and that's what happens. And when the oxygen reforms its pi bonds, the electrons are added into the carbon, like sigma star orbital, which then breaks the sigma bond between this carbon and nitrogen, and then allows the nitrogen to break off from the ring. So now we're going to get to the last step, and that's basically just forming the final products. So I think I went through that pretty quickly, but here are all the steps if you need it. An easy way to remember is pad. And here are the transition states as well as the intermediate species that were formed within the reaction. And here's the reaction coordinate diagram for this reaction. Just want to point your attention to intermediate species 2 and 5. Intermediate species 2 is higher in energy than the intermediate species 1 because you are breaking a pi bond, and 5 is greater than 4 because you're forming that pi bond. And intermediate species 4 is higher in energy than intermediate species 3 because nitrogen has a positive formal charge. That explains the relative energies. So how would we speed up this reaction? Well, we're already using catalysts, so that's one way. Another way we could do this is to increase reactants, would increase collisions that would lead to the products, or we could decrease the products that we have in the system, and according to Le Chatelier's principle, it will shift back to the products and form more products that way. There's two ways to do so. So predicting delta G and K of this reaction is actually pretty nuanced and difficult, but if you look at the reactants, you look at the products, the reactants have a ring in it, and that presents a lot of troubles. And when you break that ring and you open up that carbon chain, it's much more stable. So for that reason, this is a product favored reaction. That means at equilibrium, there's going to be more products than reactants, and K is going to be greater than 1. And according to the equation, delta G equals negative RT on K, delta G is going to be less than 0, and it's going to be spontaneous, and that's great.